Our next presenter is Emel Islamzada from Function Moz Lab. Emel, are you out there somewhere?
Yes, I am. Thank you.
Okay, over to you.
Awesome. Thank you. And thank you so much to the organizers for the opportunity to actually give this talk. And today I will be updating you guys on the research that we're doing in the lab for red blood cell deformability signatures of individual donors that are stored in the blood bag units and their corresponding segments. So next slide, please. Thank you. So one of the current challenges in the transfusion medicine still stands that not all donated red blood cells will actually circulate for the same amount of time after transfusion. And that partially stems from the fact that the term healthy donor is a very broad term. Donors will differ quite a bit and quite significantly from each other based on the demographics, on ethnicity, on sex, on a whole bunch of various reasons, which will lead to differences in post-transfusion circulation time. So and that's because red blood cells from different donors, they're different and they will store differently. We'll then go to the need for a quality control method to be able to evaluate the quality on an individual bag and individual donor level. And this is where the red blood cell bag segments come in. Segments are already produced during the standard manufacturing process. The blood from the segment is used for serological testing, and some countries also use it for hemolysis assessment. So could it potentially provide a non-destructive method to evaluate the quality of red blood cells in the bag without having to actually compromise the integrity of the bag? Next slide, please. Thank you. We're basing our studies on the fact that the red blood cell deformability is absolutely vital for its proper function, and that red blood cell deformity is impacted. So red blood cells get more rigid as the red blood cells are stored in a bag. We have an in-lab made an assay device, microfluidic ratchet device mechanism that sorts red blood cells based on how deformable they are. So the cells are sorted through the sorting matrix, going through openings, going from 1.5 to 7.5 microns, which reflects the natural restrictions that cells encounter during the circulation. And they're collected in individual outlets based on how deformable they are, which is seen in a frequency graph on the bottom left. This histogram can then be expressed as a cumulative distribution of red blood cells, which will take this data and turn it into a nice curve. And these curves can be compared. As you go towards the right, you will become more rigid. So the sample in black here is more rigid than the sample in red. From this graph, we can also calculate what we call a rigidity score, which is exactly what it sounds like, how rigid this particular sample is. And again, as you go towards the right, your rigidity score increases, the red blood cells are more rigid, which can then be used to graph something similar to the graph on the bottom right to essentially track a rigidity status of a particular sample over multiple weeks of storage. And next slide, please. Here we looked at the panel of donors. So on the left-hand side in the panel A, solid lines are the red blood cells stored in the bag, and the dashed lines are red blood cells stored in their corresponding segments. We can appreciate a couple of things just from glancing at it. One, each individual donor has a unique deformability profile over the 6 weeks of storage. Another thing we can note is in the dashed lines, the segments, not all, but in most cases, they actually closely reflect what's happening inside the bag in terms of deformability over the 6 weeks. If we look at the arrow graph on the right-hand side, we can see here the donors are also divided by male versus female, and we're seeing a summary change in deformability from day 0, day 1 to the end of storage at week 6. And we can appreciate all donors do change at least a little bit, but also male donors on average seem to rigidify more than the female donors. Next slide, please. Here we're looking at some summary data. So on the left, we can appreciate that all of the bags and their corresponding segments rigidify significantly over 6 weeks of storage. And if we look at the panel B, at the correlation of the changes in red blood cell status, deformability status in bags and segments, they actually correlate quite well. Next slide, please. In a summary, we can say that red blood cell bag units, red blood cells in different bags do have their distinct and unique rigidity score changes over the 6-week storage period. The segments in most cases reflect the changes in the bags. So the segment could potentially be a non-destructive sampling method to evaluate blood cell quality. For example, directly prior to a transfusion, but even after the transfusion, we could perhaps predict how an individual bag will perform based on how default the red blood cells from this segment are. And thank you guys very much for listening, and I am ready to take your questions.
Great, thanks very much, Emel. So again, questions can go either in the chat or please feel free to just raise your hand. So maybe since I'm already talking, I'll take the first question. I'm a little bit curious, do you see a potential application for this technology in being able to pre-identify how well a donor is going to store and then have different allowable storage lengths of time for individual donors based on the results of this kind of testing?
Thank you. That's a great question. One of the earlier studies that we did was storing the donors in particular in tubes in accelerated storage model. And in there, we actually did ask the donors to come back and to repeat donations. And what we saw that the deformability signature of a donor is consistent. If they come every 6 weeks or more in between donations, the way the deformability changes is actually consistent. So I think we do need to do more studies, but I think it is possible to identify particular donors that have particular set of deformability profiles that might be better for particular applications, for example, for long-term, for the people who need repeat transfusions and need longer circulating cells.
Yeah, thanks, Emel. Other questions? Hang on, let me see, there's something in the chat. Jill Johnson's asking if the sex difference correlates with hematocrit.
That's a wonderful question. I haven't looked at it yet, so I'll have a look at that and see if there's differences. Okay, thanks. And Jason, get your hand up. You need to come off mute.
Yep, very interesting question, presentation. I just have, I guess, a question around the applicability of this beyond products that are produced at NetCAD. We looked at this a few years ago, and depending on the manufacturing method, the product that's actually in the segment will vary from what's in the bag. So just, the Buffyco products do resemble what's in the bag, but if you go to something like a whole blood filtered product, it will be very different because of the manufacturing process. So just be aware of that. And actually that might be a helpful tool to actually look at testing this, this idea of using these segments for deformability measurements. So if you're interested, we published on this in 2014, and I'll send you the link.
Thanks,
Awesome.
Jason.
Thank you.
Cedric?
Yeah, good stuff. I guess the question is, in vitro, it looks terrific. How are you going to, or maybe not you, but what would be your projection for in vivo validation?
That's a wonderful question. One of the studies we could do potentially is take segments from a bag that has been transfused. And if it's a repeat donor, how soon do they have to come back for a transfusion? For example, if it's a sickle cell patient. And see whether what we see in a segment, whether the deformability in a segment, how it deformability score in a segment correlated somehow with how the cells actually lasted in a circulation in the actual patient. Another thing that we're doing are animal studies. So we're transfusing red blood cells into mice to see whether the rigid population of cells actually clears faster from the deformable population of cells for in vivo studies.
Thank you.
Thanks. And then Rafay Osmani has a question.
Yeah, is my audio coming in all right?
Yeah, I can hear you.
Awesome. So my question was about the microfluidic device. I was just wondering, how did you, and if this is even a possibility, but how did you account for cells that would have been lysed as they went through the constriction gradient? Because wouldn't that affect your data in terms of how many cells were actually recovered, and if that's a factor at all?
That's a wonderful question. So some of the earlier studies we've done were actually done in malaria infected cells, especially late stage malaria cells that are prone to lysis, they are quite fragile. We were able to sort them just fine and have a pretty good recovery rate for those. So I'm not entirely sure, but from my previous studies on more fragile cells and also cells that have been, for example, chemically altered, I do believe we're able to sort them fine. And also the pressure that we use to sort through the device are actually fairly low. And there's not much turbulence going on in the device either. So I believe actually our washing steps might be more likely to cause lysis than the cells going through the device itself.
Awesome, thank you.
Thanks very much. And then there's one more question here from Dr. Conway. I'm sorry, from Dr. Frysdale, asking, would you recommend ways that the segments are made, and whether that could be improved to facilitate making your measurements?
That's a wonderful question. I believe we were in a very early stages of the study, so not yet.
Okay, great, thank you.